Hello, welcome to Young's Electronics. In this video, we are going to use Norton's theorem to find the current through this 3 ohms resistor. So, the first thing we are going to do is that, according to the Norton's theorem, any linear circuit between two terminals can be replaced by Norton's current in parallel with the Norton's equivalent resistance. So, we are going to remove the 3 ohms resistor and mark the terminals. So, with that, the circuit is going to look like this. But then the first thing we have to do is to find our Norton's current, which is our IN. The IN is a short circuit current across the two terminals. So we are going to put our short circuit over here. It's our IN. And find our short circuit current that is flowing through this branch. So the current coming from the 6-volt source is, say, I1. And the current coming from the 4-volt source, say, I2. They sum up according to KCL to make I1 plus I2. And the current coming from the 5-volt source, because over here we have the negative terminal over here, the current coming from here is going to be negative. So we are going to have the negative I3 coming from the 5-volt source. So the IN is going to be the algebraic sum of all these currents. So IN is going to be equal to I1 plus I2 minus I3. So how do we find I1, I2, and I3? So when you take this loop, we want to find the I1. So to find I1, we are going to take this loop. So when we take this loop, you realize that we are going to have 6 is equal to 2 times our I1. So our I1 is going to be 3 amps. Then we are going to take this loop also to find our I2. So that's going to give us 4 is equal to 1 times the I2. So our I2 is going to be 4 amps. Then lastly, we are going to find the I3. So if we take this loop, we are going to have 5 to be equal to 1 times the minus I3. So our I3 is going to be minus 5 amps. So with all these currents, we are going to find the IN using the equation that we have up there. So our IN is going to be 3 plus 4 minus the 5 amps, which is going to give us 7 minus 5, which is 2 amps. So we already have our IN to be 2 amps. So the next thing that we have to find is our RN. And we have already said that to find our RN, the first thing that we have to do is that we are going to deactivate all the dependent sources. The first thing that we are going to do is that the next thing we have to do is that we have to find our RN. So to find our RN, what we are going to do is that we are going to short circuit all our voltage sources. So we are going to short circuit this voltage source, short circuit this voltage source, and short circuit this voltage source. Then we find our equivalent resistance. Our Rn is going to be the 1 ohm resistor in parallel with the other 1 ohm resistor, and all of that will be in parallel with the 2 ohm resistor. So this is going to give you 0.5 in parallel with the 2, and that also is going to give you 0.5 times 2 divided by the 0.5 plus 2. We are going to have 0.4 as our equivalent resistance or our Nortons resistance. So after you're done finding the short circuit current and the equivalent Nortons resistance, now we have to draw our equivalent circuit, which has the current source in parallel with the resistance, the Nortons resistance, then that also in parallel with the 3 ohms resistor that we removed earlier. We have 0.4 over here, 0.4 ohms, then our 3 ohms at this side also. So our current was 2 amps. So just like we discussed in earlier, we are going to use current division rule to find the current through the 3 ohms resistor. So that is going to give us, let's just say the current through the 3 ohms resistor is I. So that's going to give us 0.4 divided by 3 plus 0.4 times the equivalent short circuit current, and this is going to give us this as our final answer. So the current through the 3 ohms resistor is going to be 4 on 17 amps.